Good afternoon, Southminster Scholars. Continuing with our learning process of the solar system, we're going to talk about the geometry of the heavens today. I need to add to you that don't think this is beyond the simplest or my simple ability to understand the solar system. Dr. Summers is going to explain all of this in very simple terms, and you do not need to be an astrophysicist or astronomer or a mathematician to understand this series. Today we're going to talk about geometry of the heavens. The simplest explanation of the motions of the heavens, which lasted for over 1,500 years, is the geocentric one, in which the sun, moon, stars, and planets all revolved around the earth. This model in Ptolemy's Almagest is based on Euclid's Elements. We know today that this theory was incorrect, but again, we're setting a base for what we're going to learn later. So I hope you enjoy this series.
Hi. In this lecture, we're going to explore creating a scientific model of the solar system. And a scientific model must be based on observations. We're going to keep it simple and use only human eye observations, the observations you could do without a telescope. And we're going to create the kind of model that you could create yourself. We're going to follow the development of the ancient Greeks as they put together their model of the solar system, and we'll examine the perspective of an Earth-centered universe. The Earth-centered universe is really the most natural and simplest of model. We call it geocentric, geo meaning Earth, Earth at the center. And if you just observe the sky, it's the model you would come up with. This image here shows a time lapse of the sun. We see it rise in the east, we see it set in the west. It certainly looks like it's circling around Earth. At night, you can go out and look at the stars, and here's a gorgeous image of stars in the area around the constellation Orion. But if you look in the poles and you watch the stars over time, you do a time lapse of the stars, you can see that the stars also make circles in the sky all night long. So the most natural model is that everything is circling around Earth. So this would be your first initial model. The Earth would be here at the center, and all the rest of the solar system would be circling around Earth. Now, to make this scientific, we have to add in some specifics. What are the sizes of the objects? What are their distances? And how do they move? The problem with the geocentric model in modern society is not really with the geocentric model, but it's with the mythos that has developed around it. We have this idea that the geocentric model was way too complicated, that the Ptolemaic system that was developed by the Greeks started simply and then added in this feature and added in that feature, and then it needed this feature and needed that feature and needed this feature, and it sort of collapsed under its own weight. This is definitely not true. It's a nice story. It makes us feel good. Oh, we don't believe such simplistic stuff anymore. But it's a disservice to science education because the geocentric model has a lot to teach us, not only about the solar system, but also how you construct a scientific model. The geocentric model and all scientific models should be judged on whether they can account for observed behavior. Can you explain the observations of the sky? You also need to be able to predict future behavior. The simplicity and accuracy of the model that can explain observations and predict future behavior is really all that's required. One question we'll also examine today is the truth of the model really necessary? If the model can explain what we see, does it really matter if it corresponds to reality? We'll start with the basic ideas. Let's just simplify things to the Earth, the sun, and the moon. What can we tell by simple observations? One thing we can tell is that the Earth is round. Now, I know many of you were taught that Columbus showed the Earth was round when he sailed across the ocean. He gets way too much credit. Actually, it was known the Earth was round by the ancient Greeks, and Aristotle, in about 400 BCE, could offer several different arguments for why the Earth must be round. Aristotle had this thing for spheres, but he had some scientific arguments behind them. The easiest way to see it is take a look at a lunar eclipse. And a lunar eclipse is when the moon passes into the shadow of Earth. Here's an image that shows a time lapse. And on the left-hand side, you see the full moon. And as it progresses to the right-hand side, the shadow of Earth slowly creeps across the surface of the moon. And what you notice when you look at this is that the shadow of Earth is curved. And if you look at many lunar eclipses and many parts of Earth's shadow, you find that it is always curved. And Aristotle reasoned that the only shape that would always cast a curved shadow would be a sphere. And thus he concluded that the Earth was round. The moon can also be used to tell us about the relative distances to it and to the sun. If you watch the moon over a period of weeks, you see it change its phases. It goes from a crescent moon up to a half moon, to a gibbous moon, to a full moon, and then backwards through those same things, gibbous, half, and to crescent. This is caused by the changing of the angles between our direction to the moon and our direction to the sun. Basically, the lit part of the moon varies according to the moon's orbit around Earth. If you look at the half moon and think about it, it actually is a special time, because when the moon is half lit, that means the sun is perpendicular to the moon, that there's a 90-degree angle between our direction to the moon and the moon's direction to the sun. When you have a right angle, you then get a right triangle, and you can use trigonometry to deduce answers. Here's a simplistic drawing of a triangle that would be formed when the moon is at half phase. The Earth, looking directly at the moon, sees the moon at half phase. The sun would be at 90 degrees. In order to measure the sizes of the lengths of this triangle, it suffices simply to measure the angle on the sky between the moon and the sun. If you can measure that angle, which is going to be very large, almost 90 degrees itself, but if you can measure that angle, you can then get the scale of this triangle, and you can understand the relative distance to the moon compared to the distance to the sun. Aristarchus was able to do this in about 270 BCE. And I note that this was just after Euclid's Elements. The textbook of geometry was published at about 300 BCE. He got his angular measure a little bit wrong and estimated that it was about 20 times, that the sun was 20 times farther away than the moon. Real answer is it's about 400. But the method, the geometrical method, was sound. We can get the relative sizes of the moon and the sun by looking at solar eclipses. This is an image of a partial solar eclipse. And here, instead of the Earth's shadow going across the moon, we have the moon passing between Earth and the sun, and you can see the limb of the moon passing in front of the sun. It turns out, and it's a very lucky coincidence, that the angular size of the moon in the sky is about the same as the angular size of the sun in the sky, and when they pass directly in front of each other, we get a total solar eclipse. And this is a spectacular event, and during that time, the entire disk of the sun is blocked out, and you can see this wonderful corona around the sun, this amazing stuff that you can't see at any other time, at least not with the human eye. The geometry of the solar eclipse would look like this. Earth is over here, the moon is blocking the light from the sun, and we can form triangles again. There are two similar triangles here, the Earth and the diameter of the moon, and the Earth to the diameter of the sun. They form similar triangles, and because you can get a total solar eclipse where the moon just blocks out the sun, that means that the size ratio of those diameters is the same as their distance ratio. If the sun is 400 times farther away than the moon, then that means it's also 400 times bigger than the moon. A lunar eclipse can be used to get the relative sizes of the Earth and Moon. If we take a look at this image, it shows you the full sequence of a lunar eclipse. The moon starts out not being in Earth's shadow. It slowly passes through Earth's shadow and then emerges from Earth's shadow. And if you time the length of the lunar eclipse, you can estimate the size of Earth's shadow. And specifically, you can estimate the size of the Earth's shadow relative to the size of the moon. If you take a look at the geometry of it, it's really just the same thing as before. The sun casting its light, the Earth creating a shadow, and the moon moving through that shadow. Aristarchus looked at this, and he estimated that the size of Earth's shadow was about 3 times the size of the moon. The real answer is that it's about 4 times the size of the moon, but the method, again, was sound. And you're able to then tell that Earth is about 4 times larger than the moon by examining lunar eclipses. The last piece you need to complete this basic model is the size of Earth. And you can get this with a remarkable observation by when the sun is directly overhead. A man named Eratosthenes was able to do this, and he lived in Alexandria. And he noticed that on a certain day in Alexandria, you could look down an entire deep well and see the bottom. The light from the sun would go all the way to the bottom of a deep well. That meant the sun was directly overhead. On that same day, in a nearby city named Syene, the sun was not directly overhead. If you put a vertical rod in the ground, you could measure the shadow that it made. Looking at the geometry of it, you can see that the length of the shadow at Syene would enable you to measure the angle between Alexandria and Syene along the circumference of the Earth. Then, knowing the distance between Alexandria and Syene, you could calculate the full circumference of the Earth. And he was able to do this and get a very accurate estimate for the size of Earth. Combining these pieces of information, you get the size of Earth, then you get the size of the moon and the size of the sun, and from that you get the distances to the moon and sun. And you end up with basically looking at eclipses and observations of the moon and sun. You can have a full model of Earth, moon, and sun. To make this into a more complete scientific model, you'd also want to look at motions. And motions can provide a basic way on how to order the distances to objects, the sun, the moon, and the planets. If we look at the periods of the various objects, the moon goes through its phases in about 27 days, about a month. It's the origin of the month. Mercury, about 3 months. Venus goes through its period in about 3/4 of a year. The sun in 1 year. Mars about 2 years. Jupiter 12 years. And Saturn about 30 years. Though we don't know at this point from the human eye observations the distances to the planets, we can get the distances to the moon and the sun, we can estimate which one is further away than the other from their motions. It's really just basic idea that something nearby will move across your field of view at a faster speed than something far away will tend to appear that it's moving slower. So the basic structure, the ordering of the planets, was determined by the periods. And so in the geocentric model, the Earth was at the center, and the planets were around it, moving at slower and slower speeds. The moon, then Mercury, Venus, Sun, Mars, Jupiter, and Saturn. Now, I've drawn them here as circles, and that would be the basic way you would model them, but the motion that they make across the sky is not constant. It's not uniform circular motion. The speed varies along its orbit, and we can tell that by looking at the sun's motion. the sun's motion can be measured by the seasons. And the seasons are basically spring, summer, fall, and winter. They are measured by the equinoxes and the solstice. The equinox being the start of spring, the vernal equinox being the start of spring, the autumnal equinox being the start of fall, the summer solstice being the start of summer, and the winter solstice being the start of winter. And they, as you can see, they occur in March, June, September, December, approximately 3 months apart. And if you look at that in a diagram of the sun's motion around Earth, the solstices are opposite each other on the circle, and the equinoxes are opposite each other on the circle, and they divide the circle into 4 equal parts. If the sun were undergoing uniform circular motion, then the length of each season would be about the same, 1/4 of a year, or about 91 days. However, when you look at the measured time for the seasons, you can see that they are not the same. In this table, I've added in the length of the seasons, and spring is 92.8 days, summer is 93.7 days, fall is 89.8 days, and winter is 89 days. The length of the seasons is not the same, and therefore the sun cannot be going through uniform circular motion. How are we going to model that? Well, we're going to look at the model created by a man named Ptolemy. And this is a drawing of him. And it is called the Ptolemaic model, but that's really giving him a little too much credit. What Ptolemy did is he took about 500 years of Greek astronomical knowledge and organized it and put it into a systematic presentation. He based the geometry of it upon that found in Euclid's Elements. And we're going to look at how they solved these ideas of creating the motion. So if we look at the sun's motion and the real seasons, we can see that summer is much too long for this arc. This arc needs to be longer. And winter is too short for this arc. Winter needs to be shorter. How would you reconcile that? Well, they came up with the idea that we're going to preserve uniform circular motion for the sun, but we're going to move Earth off-center. If you take Earth and shift it off-center, and then the solstices and the equinoxes shift with it, you can see that you can create a much longer arc for summer and a much shorter arc for winter. And you can justify the lengths of the seasons by uniform circular motion seen by an observer who's not at the center. Now, this is a little bit exaggerated here, but we have a more accurate model to show it to you. This is the motion of the sun in an eccentric circle. The observer is located here at O, and the center of the circle is actually at Z. The green line is the motion of the sun circling around Z, and the blue line would be the mean sun, the sun as if it were orbiting around the observer at O. Now, if I put this in motion, you can see that the green line and the blue line move at different speeds. When, if I pause it here, when the sun is closer to the observer, the green line catches up with the blue line. It moves faster and actually gets ahead of it. Then, as the sun gets further away from the observer, the blue line catches up to the green line, and the sun observed in an eccentric circle moves slower. This is what the eccentric circle allowed us to do. It allowed for the sun to move faster when it was closer to the Earth and move slower when it was further away from the Earth. So the eccentric circle could explain the motion of the sun. What about the motion of the moon? Well, it didn't quite work for the motion of the moon. For that, we needed a different geometrical construct called epicycle and deferent. And these are really cool words, and they're a little bit scary, but they really are a concept you already know. If you think about a star and a planet orbiting around that star, and then a moon orbiting around that planet, you already know epicycle deferent. Because this construct of one object orbiting another, orbiting a third, is exactly what epicycle deferent is about. We just have to take this diagram and relabel it. And for epicycle deferent, we have Earth at the center. The deferent circle is the first circle around the Earth, and the epicycle circle is the second circle around the point on the deferent circle. We're doing uniform circular motion both in the deferent and in the epicycle. And this was used by Ptolemy in order to create a basic moon model. And we have that for you here. The observer, again, is at O. C is the point moving around the deferent circle, and M is the point moving around the epicycle circle. And you can see that it makes a interesting motion. But if I only turn on the trail, because when you think about it, epicycle and deferent could produce some very complex motions. But the motion done for the moon here, as the trail makes its first orbit, you can see produces a relatively smooth orbit. Relatively smooth here. And you're able to create a nice orbit for the moon. Unfortunately, it doesn't explain the full motion of the moon. A single epicycle really couldn't explain the speeding up and slowing down of the moon through its orbit that we observed. Instead, he found he needed to use 2 epicycles. This is the diagram of Ptolemy's full moon model, and it's a little complicated. We have the observer here at O. We have the first deferent circle at Z. We have the epicycle around Z, C, which is also serving as a second deferent circle. And then we finally have the epicycle M moving around the point C. The strange thing about this model is that the interior epicycle is rotating in the opposite direction of the exterior epicycle. And so the motion is kind of funky. Matter of fact, they refer to it as the crank mechanism necessary to get the moon's motion. Let me turn that on. Now you can see the motion of the moon on the exterior epicycle, and then it moving around the interior epicycle, and it's a little bit complex. If I turn on the trail, you see that once again we have a relatively smooth orbit, even though it's got a relatively complex behavior behind it. Okay. So you can see that the moon was modeled by a double epicycle deferent because it had a much larger variation in its motion between its slowest point and its fastest point in its motion. The interesting thing about the epicycle deferent is that it's actually equivalent to the eccentric circle. You can construct an epicycle deferent to exactly match the eccentric circle. And I go back to the sun model, and you'll notice down here I have a slider that I can go to the eccentric version of it. And so this is the eccentric version of the sun. But I can also take this slider over to the epicycle version of the sun and produce exactly the same motion. A properly configured epicycle deferent, in which the rotation of the epicycle exactly matches the rotation around the deferent, can produce the same motion. And you can see that clearly when I put the slider halfway in between. And in that case, you can see both the epicycle and the eccentric circle produce the same motion for the sun. So the epicycle deferent is sort of like a generalization of the eccentric circle. There's still one more geometrical construct that we need to finish off Ptolemy's model. It's called equant motion, and it's sort of like an extension of the eccentric circle. This diagram here shows you circular motion, and the motion, the time it takes to go between any one of these sections is the same. That's basic circular motion. Then we can think about having that motion with respect to an off-center point. If we move the center of the circular motion off from the center of the circle, then you can see these top arcs are shorter than these longer arcs. And if it still takes the same amount of time to go between any of these 2 points, then the planet must be moving slower between T1 and T2, for example, than it would be moving between T4 and T5, because it has a shorter distance to cover between T1 and 2 and a longer distance to cover between T4 and T5. Equant motion extends this just like a little bit further by also moving the observer off center. And so the center of the circle is here in this gray dot, the center of the circular motion is this unfilled dot, and the observer is here in this blue dot. The result of which is the equant motion observed by the observer has a very strong differential from one side to the other. You can see that the distance here between T1 and T2 is much, much shorter than the distance between T4 and T5. Again, when the object is closer to the observer, it moves faster. And when it's further from the observer, it moves slower. So we've got the sun and the moon, and now we're going to add in the planets. The planets were modeled with the equant motion and the epicycle deferent. You need the epicycle deferent because you've got to explain this strange motion of the planets. The derivation of the word planets is wanderer. They were the objects that wandered across the sky. The sun and the moon always moved in the same direction across the sky and never in the reverse direction. The planets did not. Mercury and Venus, shown here, would always be found near the sun. Whenever you see a picture of Mercury or Venus, you're going to see it at twilight, either in the evening or in the morning, because it's always found within a certain angular distance from the sun. Mercury about 28 degrees and Venus about 46 degrees. And their wandering motion is that they would wander back and forth on the sky around the point of the sun. You would never find them opposite the sun. They would always be over in the same region of the sun, wandering back and forth. The other planets, Mars, Jupiter, and Saturn, they showed a different kind of wandering motion, something we call retrograde motion. And here's a diagram of the path of Mars in a retrograde motion. And it is moving across the sky in the normal direction, same direction as the sun and the moon move across the sky. And then it slows down and stops at what we call a stationary point. And then it backs up and goes backwards relative to the stars, hits another stationary point, stops, and then moves forward again. And this retrograde motion was found to occur when the planets were opposite the position in the sky of the sun. If the sun was over here and Mars was over here, that's the time that Mars would go through retrograde motion. And so with the equant and the epicycle deferent, you're able to model these motions for Mercury and Venus and for Mars, Jupiter, and Saturn. This is a model of the motion for Mars, Jupiter, and Saturn. And the observer here is at O. The center of the deferent circle is at D. The equant motion offset is E. The center of the motion on the deferent circle is C, and the planet is moving at P. Let me put this in motion for you. And you can see it basically looks like the basic epicycle deferent. You can't really tell that the center of the circular motion is at the equant point. It looks pretty much like a standard epicycle deferent. The important point for these exterior planets is that when they come in the inside part of their epicycle, they make that little curlicue. Right? This is the time when you would see the retrograde motion. The proper ratio of motion around the epicycle with motion around the deferent produces these little curlicues and produces the retrograde motion on the sky. It also shows you why Ptolemy is famous. He invented spirograph about 2,000 years before it came out as a kid's toy. Now, this is how they produce the entire model of the solar system in the geocentric model, using these three basic geometric constructs: the eccentric circle, the epicycle and deferent, and equant motion. And so to put it all together, we have a complete model of the Ptolemaic solar system. And so here we look at this, and on the exterior we see the sphere of the stars, which is basically unmoving in this. And the blue represents Saturn, the purple represents Jupiter, the red represents Mars. And we've got a wonderful slider down here where we can move in closer because the scale of this is much, much too large to look at in one thing. And we move down, we see this, the sun here in blue. We see Venus here in green. Going in further, we see Mercury here in red and the moon here in blue. And way down deep at the center, we find the Earth. And the person who created this model was cute. He added in Ptolemy's map of the Earth. This is a map produced by Ptolemy as a texture onto the Earth. So let's back out a little bit and put this in motion. So here you can see the moon working with its crank mechanism and its double epicycle deferent. And as we pull out, you see Mercury in red moving with its epicycle deferent, and then to Venus in green working with its epicycle deferent, and the sun moving in its eccentric circle. One thing to notice is that the epicycles for Mercury and Venus, Mercury in red here and Venus in green here, are always aligned with the sun. The motion on the epicycle allowed for this bounded elongation of Mercury and Venus, that the planets would be able to go in front of the sun and behind the sun as long as the center of the epicycle circle always pointed toward the sun. So the model naturally is tied to the sun and explains the bounded elongation. We move further out. We see Mars in red, Jupiter in purple, and Saturn in blue. And let me speed it up a little bit. And you can see the eccentric motion of the epicycle, the sort of the curlicue motion. The other thing you want to notice, if I pause it here, is that the position of Mars, Jupiter, and Saturn in their epicycles are tied exactly to the position of the sun relative to Earth. That allows the retrograde motion to occur at opposition. Put it back in motion again. And you can see that the motion on their epicycles is tied to the sun's motion around the Earth. When viewed in this manner, the full Ptolemaic model looks very complex. But the secret is that its complexity derived from simplicity. Remember that there are just 3 geometric constructs that underlie all the motions observed in this model. And in that manner, and in many other respects, this should be considered a triumph. Not just because you can create a complex model out of simple ideas, but because this was the first time that the motions of the heavens had been scientifically predicted. And it could not just predict the motions of the planets and the sun and the moon, it could also predict other events like eclipses, which had never been able to be predicted before. Ptolemy did not think this was a real physical model, but rather just a mathematical device for predicting. He entitled his book Mathematical Systematic Treatise. It was later called Almagest by Arabic astronomers. This geocentric model provided accurate enough predictions that it remained the standard for 1,500 years. The only work I know of that lasted longer was Euclid's Elements, which was a standard textbook of astronomy well through the 19th century. Matter of fact, the geocentric model is the model you would derive today if you just based your observations on what the human eye could see. You would come up with a model like this. And that shows a basic tenet that underlies astronomy and all of science, that the universe is understandable, that it's explainable, and that it is predictable. That is the construct of science. However, this model leaves one question open. Is mathematical prediction enough? A scientific model that can explain the observations is great, but one that actually represents reality would be better. Does a model actually have to represent reality, or is just the mathematical prediction enough? We'll explore that question in our next lecture. Until then, have a great day.
Ground control to Major Tom. Ground control to Major Tom. Lock your Soyuz hatch and put your helmet on. 10, ground control 9, to Major Tom. 8, 7, 6, commencing countdown, engines on. 3, 2, detach from station and may God's love be with you. This is ground control to Major Tom. You've really made the grade, and the papers want to know whose shirts you wear. But it's time to guide the capsule if you dare. This is Major Tom to ground control.